Our first speaker is Johannes Jakob Meyer, and he will talk about quantum metrology and financial regime.
Yeah, I also want to thank the organizers for the opportunity to speak here and for organizing this wonderful workshop. And today I'm talking about a more exotic topic, I would say, for this kind of workshop, mainly about quantum metrology, but it's still in the financial regime, so I think it fits a bit quite well. And this talk is based on our recent preprint of the same name, and which was done with this wonderful people. We have Subi, Daniel, Nancy, and Philippe, who's also here in the audience, and we can also work for questions. I also put a QR code, but these slides will also be available on the website, so you don't click on it now. But I'm obviously very happy if you have a look at something. Okay, so what is quantum metrology? The traditional setup, and the one that I'm using in this talk, is the following. So you assume you get like a parameterized ambient state. In this case, you have some parameter t, which is probably continuous, and it's just like a generic parameter. But you can think of it, for example, as time. So this might be an instance of an atomic clock, for example, and you really want to tell the time quite well. And to do so, you have to perform some sort of measurement. So you take your state, you measure it in some basis, and then post-process this measurement outcomes into predictions of what the time actually is, what we call the head. And from a fundamental point of view, you can just include all of this measurement post-processing into a POVM. So, and in the traditional approach to quantum metrology, we want an unbiased estimate. So on average, I want to be correct in my estimates of the time, and we want to have low variance. And in this scenario, we have the so-called Pomerol bound. And it tells us that the variance of this estimate is lower bounded by the inverse of this quantity, curly f, which is the quantum Fisher information. And this quantum Fisher information, it arises if you have a look at the quantum fidelity of close-by states and do second-order expansion. So this quantum Fisher information really governs how distinguishable closed states are in terms of quantum fidelity. And the nice thing about this Pomerol bound is that it is achievable in certain limits. And this means that if you want to know about the precision of measurement in this approach, it suffices to calculate one number. And it's nice because it reduced all this complicated problem of how to do this estimation into calculating one number. Yeah, so this means that in the traditional approach to quantum metrology, it has kind of, in a certain sense, become a study of the quantum Fisher information. So you take a problem, you calculate the quantum Fisher information, and then you kind of already know kind of the best achievable asymptotic precision. But there are some catches. So the thing is that you see that on the left-hand side of this inequality, there's variance. So it's like in itself an asymptotic concept. And also on the right-hand side, there's this quantum Fisher information, which is also asymptotic, but it's just like for asymptotically closed states, right? So there's like two asymptotic things appearing here. And things bound also assumes that you approximately know what the actual value of t is, the true ground truth, because it appears on the right-hand side of the input. And as such, the application of this bound is hard to justify in the finite regime, and we also give like an example of this where we mathematically see this in our paper. Okay, so what do we want to do differently in like a finite sample set? So we say instead of looking at variance, can we look at outputting an estimate which is within a certain prescribed estimation tolerance delta. So you fix delta and you say, okay, is it in this tolerance window around the true value or not? And if this is the case, we say the estimation was a success, and if not, then it was a failure. And this, if you take this quantifier of success or failure, then you can ask yourself, okay, but what is the probability of getting like a successful estimate? And so I put the setup here a little bit more compactly, and if I ask you, okay, what's the probability of a successful estimate, you have to ask yourself, okay, probability with respect to what? So obviously there's like an inherent randomness in measurement, but I mean there should be something more. And one way of treating this is to assume that the underlying parameter is distributed according to some higher distribution, and which leads you to a definition of Bayesian success probability. And here you kind of see this expression. So on the right-hand side, the trace rows of t, q, t of t tau. It's just like the probability of estimating t plus tau for the parameter as a t hat. if the underlying ground truth was rho t, then we integrate out everything that is in the kind of successful estimation region, and then you take the average over prior. But assuming that you have like prior knowledge about the distribution of the parameter is often just like not possible. And in that case, you want to do something that is independent of the possible priors. So you also look at the scenario where you have an adversary that chooses, so you fix a measurement, and then the adversary chooses the kind of worst case ground truth that is possible. And this gives you a notion of minimax success probability, where you just like minimize the right hand side. And the nice thing about like this minimax success probability is that you can guarantee it against any possible prior distribution. So you really don't need to know what the distribution is and what is actually happening inside the experiment, what the state of T actually is. Okay, but I mean, this is like something that's probably more an explanation for the metrology people, not for the statistical people here. Okay, good. You see these definitions, and the first thing is that I left this POVM arbitrary. So you have some Q, but obviously you want to know what is optimal Q. So what is optimal POVM? So we just like define a version of this minimax success probability. So I will focus on the minimax case the rest of this talk because it's also usually the results look better and it's easier to explain intuitively. Okay, so we define like a version of the star, which is just like optimized over all possible measurements, over all possible ways of predicting the parameter. And what we show in our paper is that this constitutes a so-called semi-infinite program, but you can just like think of it as like an STP, but your variables that you optimize over RPMs. But at the end of the day, intuitively, there's not so much of a difference. And we show that we also have like a dual formulation, there's no duality gap. We also generalize this to the case where we don't have like a parameterized state to go with, but the parameter is really encoded in like a quantum channel or multiple copies thereof with maybe different access models. So you can also have this semi-infinite programming formulation, for example, if you have a quantum proof, if you have like really adaptive access, if you have this indefinite post-order access, these kind of things. And what we also do is a more applied thing, where you say, okay, I want to go to an experimentalist and say, please do this POVM, and then you say, I cannot do POVMs, I can only do detection or something like this. And I say, okay, we also look at this case, we say, okay, we fix some sort of measurement, some POVM, and then we only ask what's the optimal way of post-processing the outcomes of this POVM into predictions. So we also have some results on that, which are also in the Bayesian case optimal. Good. Now, the core contribution of our work, which is kind of long, is this, that we can connect this problem of estimating a parameter to hypothesis testing. So I actually want to show you the proof because I actually relatively simple. So imagine you have this metrology problem, you have your constant your continuous parameter t, and you're given some of these states, rho of t1. And for given POVM, it produces some estimate of the parameter. You know that with a certain probability eta bar, so this like minimum success probability, it will be within like this allowed tolerance region, right? And because it's minimax, this also holds for these other states, like any states that I can put on this line. And now I chose those states such that these like delta intervals that don't touch. Okay. And now I say, okay, it holds for all of these states, but what if I just like forget that this was a metrology problem and look at it as a multi-hypothesis testing problem? So I'm now tasked with somebody who gives me these three states to say which one is it. And then I can remember again that this came from like a metrology problem and where the things were well separated. And then I know that if I do a very simple strategy, I just like measure the metrology POVM, get an estimate, and then just like predict the TI or the TI, which was closest to the estimated value, then I can still guarantee the same success probability because this interval did not touch. Yeah? If those intervals would touch, then there would be some ambiguity and I would not be able to guarantee anything. But in this case, if these intervals don't touch, then I know that for this multi-hypothesis testing problem, I can guarantee the same minimax success probability. And this is kind of already the statement of the theorem. As long as you, also if you have a metrology problem, let's say on the real line, and if you put your states such that they are well separated with respect to the tolerance, then the associated multi-hypothesis testing problem success probability upper bounds metrologic success probability, because you can use one to solve the other. And in the Bayesian case, it looks a little bit more ugly, but this is the basic thing. So what we also do is we cannot generalize this, because this is like for the univariate setting. We also have results for, like, again, for channels. We have results for Kunz. We have results that generalizes to like arbitrary parameterization space with arbitrary distance measures. And what this kind of gives you is like, in a sense, a generic reduction of like metrology problems / also learning problems to hypothesis testing. So, for example, we heard today already about like this Lecam's method, for example, where you say the underlying technique is you want to find two things which are kind of far apart with respect to your tolerance, for example, but they look very similar from the point of view of your actual experiment. And we can do something similar here and apply our bounds to this problem. Okay, so we have this reduction of our metrology problem to hypothesis testing. And what we can do with it is we can look at the asymptotics. I know this is beyond IID, but I still hope we have some love for asymptotics. So the thing is, what we can define is an asymptotic rate. So we fix the tolerance delta, and then we let a number of copies that we are given go to infinity and ask ourselves, okay, how quick does the success probability approach 1? And this hypothesis testing reduction immediately implies the following upper bound. So we just like take the worst pairwise rate of hypothesis testing between states which are sufficiently well separated. This is like the more or less trivial part that flows from the previous result. And what we also give is like an achievability statement. We don't have like full achievability. This is sorry. So we have an achievable lower bound, which is not this, because this is proved to be extremely tricky to achieve, but we have something else. So here I define you something which is the hypothesis testing rate. So we want the hypothesis test rho t versus rho t prime, but you fix a sequence of measurements. And then you say, okay, what's the asymptotic rate with this fixed measurement sequence? And then the thing is that we want to have like a supremum over all such measurement sequences, but it has to optimize it simultaneously for all possible pairs of states. So because we cannot exchange these limits, we do not achieve this asymptotic rate. However, the nice thing is that in the classic case, we know what the measurement sequence is optimal for this case, because we can because there's essentially no basis to measure in, everything is just like already diagonal. So what we get is that this asymptotic rate can actually be achieved in the community case. So at least in the classical parameter estimation setting, we know the asymptotic rate of how quickly we achieve unit success probability. Okay, so next, the thing is that so far I looked at success probability, but fixed the tolerance at a constant value. But in practice, and people often care about the reverse, where they say, okay, how small can I make the tolerance while still guaranteeing a certain success probability? For example, I want to be successful in 99% of the cases. How small can I make the tolerance? And this deals with kind of the reverse definition, where I say, okay, you take the same expression that we had before, but now you optimize over the tolerance parameter, and you say, okay, I still want everything to at least give me this success probability, and then I take the smallest one of those. And this is also more in line with what metrology people commonly do, because in the Common-Raum bound, you saw that like people lower bound the variance, which amounts to lower bounding standard deviation. So this is also like a sense of like how small can I make a certain tolerance on an intuitive level. Okay, and what we do in this setting with this tolerance is that we give like a finite sample analog of this Common-Raum bound. So recall the Common-Raum bound, and now I just took the square root such that the standard deviation appears here. And what we give is a bound of the following form. So we have that our minimax estimation tolerance at fixed success probability has no bound of the form. Only there's one term which only depends on the failure probability, and there's one term which depends on the failure probability and this constant q here, or not constant, this parameter q here, which in the i.i.d. case is going like 1 over square root n. In the initial version of this talk, which was 10 minutes long, I had 5 slides explaining what q was. But yeah, if you are interested in that, I can also explain to you the afterwards. But at the end of the day, it kind of measures how close we are to like an idealized setting where this problem is kind of easy to solve, but I can explain to you. And here we also have again the quantification information, but minimized over t. So the thing is that how does this come about? Basically, we use like a lower bound for the binary hypothesis testing error probability, which is given to fidelity, and you can also do all these tricks with Taylor expansions and these kind of things. And then, but I'm happy to play them afterwards. Okay. Now, having seen this nice and around, I just want to summarize again what we actually propose as like a framework for quantum metrology. So quantum metrology, as I said, normally people will just like using invariances, but in the finite sample regime where you only have a few copies, you can be interested in more things. And I already told you what the success probability is. It's the answer to this question of, okay, what's the probability of obtaining an estimate within a fixed tolerance? We also ask ourselves, okay, what's the smallest tolerance that still guarantees a fixed success probability? And at the end of the day, you can also ask a third question. So if I care about both things, then I can ask about the sample complexity. So how many copies of the state do I have to take to guarantee a fixed success probability and at a certain tolerance? Yeah. And I also want to emphasize that we are not the first ones to come up with some of these definitions. I mean, these have also appeared in many prior works, for example, also by Hayashi, and all these people. A lot of people have been working on this, but I would say that we are the first to assemble them in like a coherent framework to really just treat quantum metrology in the finite sample case, and our technical results about those quantities, I would say, go well beyond the prior art. Okay, so, and with that, I also want to mention some further results that we have made, because it's very long. Yeah, so the thing is, we also have an application. I mean, it's a metrology paper after all. So what we do is make a finite sample analysis of phase estimation. Phase estimation, you can imagine you have like a couple of spins, and on every spin we have like a phase performance, so like a 40Z application, for example, acting. And then the question is like, how well can I estimate this phase? And for this particular problem, it has a lot of symmetries. We show that the critical measurement is actually a minimax optimal measurement. This allows us then to get a closed-form solution for the minimax success probability, which in turn allows us to optimize over the input state and characterize the optimal probe states and the optimal entangled and non-entangled rates for this problem. And I mean, I also have to say that all the heavy lifting in this problem is like saying that the PGM is optimal. The rest follows from like known research from the 70s and 60s process. Okay, then what we also have, we have like a chapter on connections to single-shot entropy measures. For example, this optimal Bayesian success probability. It is kind of can be seen as conditional entropy. And we also have connections to hypothesis relative entropy. Then also, as I said already, we lift this hypothesis testing connection to channels with different access models and to arbitrary parameterizations. And we also have many other extensions. For example, Timon today talked about like this idea of property testing. You want to estimate the property of a state, for example, and we also, for example, show how we can do this by introducing nuisance parameters into the problem, and then we can also use this framework to study this. And we give an overview of the many open questions that we still have here, and I also want to do some type here. So first, one very nice open problem is just like to find generic measurements that give a good out-of-box performance. So if I give you any kind of like sensing problem, any kind of sets of states, is there like a generic lower bound for the success probability by using a certain measurement? And I mean, the obvious candidate for this would be the critical measurement, but it's just like notoriously difficult to work with, especially in this continuous setting and if there are no symmetries. Yeah, so this is one question. Then we also want to have improved version of these finite sample analogs for their Raw bound, because, for example, I don't know if you noticed, but in our bound the correction was in the negative direction. And I actually would like to have a correction which is positive direction. So we want it to be harder for finite sample. So these things, I think they can be much improved, but I think these things also hinge much on a better understanding of like hypothesis testing and multi-hypothesis testing in the finite sample regime. So there's also a lot to be done on that front, just like improving converse bounds for multi-hypothesis testing. then we want to better understand the advantages of actually using adaptive processing and containment when estimating parameters. And I would still be very much interested if we can improve or disprove a general achievability of this asymptotic rate that we had, that I already presented you in this talk, because on an intuitive level, I think it makes a lot of sense that asymptotically estimating a parameter over an interval should be as hard as like the hardest distinguishing problem between two states which are sufficient far apart. I mean, on an intuitive level, it makes a lot of sense. But proving it is kind of tricky. Yes, and another very interesting problem, in my opinion, is this idea of like mixed asymptotics. So to say, like a Höfting setting of this metrology problem, where you say, okay, I want my tolerance to decay maybe as 1 over square root of n, or a little bit slower or something like this. How fast can I, in this setting, make the success probability go to 1? Or if I say something like a strong converse, if it decays faster than like an admissible scaling, that the success probability has to go to 0. These kinds of things. So I think these are also very important open questions, especially in the channel setting, where we know that for different classes of channels, different scaling regimes for this tolerance parameter are like possible. So for example, there's this delta going like 1 over n scaling, the so-called Heisenberg limit, but if your channel is noisy, this is not achievable. Sometimes there are even intermediary scalings. So I think there's a lot of very interesting physics/information theory to be found in these like scenarios. And yeah, so the summary of this talk. So we have these new tools, these new frameworks, these new bounds to understand quantum metrology in this new short finite sample regime. This framework that we have is very close to quantum information theory, as I hopefully made clear. There's a lot of connections to hypothesis testing going on, and it's both in the tools we use as well as in the results. And we really have a plethora of open questions. They range really from practically motivated ones, like these out-of-the-box measurements and like what can I do in practice, to these completely information theoretic questions of like, is this rate achievable? And this makes this like finite sample regime an exciting opportunity for quantum information researchers and theorists to really make a mark on the small applied setting of quantum metrology. So I mean, basically, I'm right now a salesman, so not like Bartosz, who is trying to sell you the generalized quantum science number, but I really want to sell you finite sample metrology, and it has the advantage of if you write ground proposals, you can now say that if you do hypothesis testing converses, you're doing something which is applicable to this. So this is really, yeah, maybe helpful. And with that, I would like to thank you for your attention and happy to take questions.
We have 3 times of subjects.
So I'm wondering about, you showed at some point in the asymptotics, a Chernoff bound and corresponding achievability.
Yes.
So this achievability is for the metrology problem, right?
Yes.
So I'm wondering how you go, so you showed how to go from a metrology strategy to a hypothesis testing.
Yes.
How do you go back? So how do you go from a, because this is a Chernoff bound, so how do you go back from a hypothesis testing strategy to a metrology strategy where you have to distinguish really?
Yeah, so at the end of the day, what we do is we have this, I told you about the setting where we fix the measurement and we show it optimal post-processing estimation setting. And essentially it hinges on that. So basically what we do is we take first this continuous metrology problem and reduce it to like a discrete problem, which is like Andreas told you, like this decoding. So you want to have like, say you have 10 states on a ring and you want to hypothesis test yourself, but not from everybody else, but everybody else but your immediate neighbors, for example. So this is the problem we reduce to. And in that problem, we can show that like an analog of maximum likelihood estimation is kind of optimal innovation setting, and we can then use some actually super simple manipulations, but which are kind of, it felt like a nice trick at the time, to basically reduce this to the pairwise hypothesis testing error. So it's not like we use like a hypothesis testing protocol to get to construct a metrology protocol, but we are really doing, let's say, a metrology protocol and just say that the errors relate to the binary hypothesis testing errors.
So basically, you're using the upper union bound reduction.
You mean the upper bound, the sphere? Yeah, I mean, I don't know if it's union bound, but I mean, I think like it's relatively generic. So this like connection hypothesis testing, it really echoes like this general construction that you want to do to achieve like standard complexity or success probability bounds. I mean, it's like you take some problem and reduce this to like a decision problem, in this case hypothesis testing. And what people normally do is they take this again and then they apply some of these like out-of-box tools like Johannes or Arno, and then you get like really bounds on the error. But yeah, basically the reduction to hypothesis testing is like a core thing, but as I said, it's like a generic.
Questions? If not, let's think.